Welcome everybody. Made it. It's the last session of Activate, and we're going to talk about Fusion and Kubernetes. The keynote. No? Yeah. What do we got? Okay, so we're going to do a quick intro, and then we're going to talk about our journey with Fusion and Kubernetes at Lucidworks. We'll go back in the past a little bit and talk about the beginning, where we're at now, and then what's coming in the future. Quickly, I am Alan Eugenio. I'm the Senior Director of Engineering Services at Lucidworks.
I'm Joe Streeky. I host the managed platform, all of our managed platforms at Lucidworks.
And Joe has also managed solar at scale at Career Builder for many years, so lots of expertise there. I'm assuming everyone has heard of Lucidworks Fusion at this point. We will do a quick, again, it's a data platform for both AI, search, ingestion of data. You can build apps or data-driven apps with App Studio, and I'll stop there because I'm sure you've heard this a few times at this point. So, Kubernetes. Who knows, or let me say it this way. Who's using Kubernetes today? You raise your hands. Okay. Who's got it in production? Okay. Yeah, the next question. Who's got solar on Kubernetes? Anybody? Fusion? Okay. So we'll start with the Lucidworks journey here. So I want you all to think back to September 2016 timeframe. That's when we started working on containerizing Fusion and also integrating with Kubernetes. So remember, back to that point in time, there was still no Docker for Mac. This was kind of not the early phase, but it was maturing. So you still had to fire up a VirtualBox VM, use Docker machine, boot to Docker, all that fun stuff, just locally. Kubernetes was in 1.6, so it was maturing, but not quite where it is today. So an example of that, when we started trying to do stateful and persistence, we were using pet sets in alpha. Pet sets, for you that may not know, was the precursor to stateful sets. We also were using AWS, and just to get a Kubernetes cluster up and running was not an easy task at that point in time. And so we had a few options. One was COPS, which is Kubernetes operations, an open source library or set of utilities for deploying an opinionated Kubernetes cluster to AWS. Or you could roll your own using Kelsey Hightower's Kubernetes the hard way as a model. We chose to use COPS, and it's been great for the most part. But this is where I would encourage any of you guys that aren't onto Kubernetes or in production with it quite yet, I would encourage you all to use a managed Kubernetes offering at this point. All the major cloud providers have them. They are able to keep up with releases, Kubernetes releases, much quicker than the COPS project. COPS does a great job, but it's just 3 or 4 guys in the open source community. So one of the things we've run into in production is, hey, we want to get to the most recent version of Kube because it has new features and bug fixes for, let's say, volumes around stateful sets and using EBS. And we've had to wait for a long time for COPS to then roll the next version and get there. So again, if you guys can be on a managed Kubernetes offering, I would highly encourage it. Also, at this point in time, going back, Kubernetes it hadn't won the container orchestrator wars yet, right? So we discussed internally Kubernetes versus Mesosphere, or Rancher. Like, those were all the kinds of options and things on the table at that time. We chose Kube. It was cloud native, container native, whereas the other things really were not for the most part at that point in time. So, and also just the Google backing, and it just made a lot of sense. It seemed to be where everything was gonna at some point coalesce, and eventually it did. Let's see. So how did we approach containerizing Fusion and then getting it to Kubernetes? So we use a pattern or a strategy I call crawl, walk, run. So we started small. We said, let's get Fusion to run inside of a single container. Obviously, that goes a little bit against the mantra of Docker at the time, which was single process, single container. They've backed off that a bit, but we did. So we would get Fusion to run all the services in a single container. The next step was, okay, how do we go ahead and start isolating all of the Fusion services into their own containers? And so just the path of least resistance at that point was, let's get a Docker Compose and just get that to work locally. And then once we got kind of through that exercise, it's like, all right, now let's do the same thing. Let's deploy into Kube. What do we do? And so we're like, all right, let's follow kind of the same model. So now let's just take our single container of Fusion and make that a pod and deploy that. And we got that to work. And then now let's actually take all of our isolated services and turn those into pods themselves. You end up with a whole lot of kubectl scripts and YAML files and things, and it gets kind of messy. And so the next step was to find something to kind of help organize all of that. And that's where Helm came into the picture. So we'll take a quick pause here and talk about what Helm is. Helm is a package manager for Kubernetes. To use their words, a Helm chart will help you define, install, and upgrade even the most complex Kubernetes applications. Fusion definitely qualifies as a complex application, and we'll talk about that in a minute. So what a Helm chart is a set of templates that allows you to really think of your application as a single unit of work. So you would take all of those isolated pods, the set of pods that we had before, and think of that as a Fusion cluster, as opposed to just a set of pods that weren't really related. Helm also gives you the ability to run a single CLI command. So example here, Helm install Fusion tarball, and you can do things like run a dry run and see what might happen in your cluster by running these commands. Then you can do a Helm list, upgrade, delete. There's various ways of managing your Helm chart instances at that point. It's also worth calling out, Helm has two parts today. There is Tiller, which is run on the server side. So you deploy Tiller into your Kubernetes cluster, and then you run the Helm CLI, and it talks to Tiller. There are some security concerns around that, that the next versions of Helm are going to address. So the Tiller component is going to go away with, I think it's Helm 3. Yeah, so just as I know not all of you are there and might not be using Helm, but just as a heads up for that. So let's come back to Fusion being a complex stack of services. So starting at the top, we have Zookeeper, Solar, Connectors Classic, and these are highlighted because they're stateful. So meaning we actually write to disk and we want to keep persistence around. So, or we want to keep the data around. Then running through the rest of the stack, we have our API service, which is really used for processing. Connectors SDK and Classic are both used for ingestion of data. Proxy is for security. UI hosts our admin UI, Insights, and App Studio applications. Web Apps hosts the apps that are generated by App Studio. And then we get into the analytics services, Spark Master, Worker, and the SQL engine. It's also worth calling out at this point, and in particular for the stateful ones, just in general, stateful applications is still hard and an evolving technology in the container world. This is not unique to us. Go run Elastic or Mongo or any database. All of these applications have the same kind of challenges still. It's evolving. 1.12 of Kubernetes introduces some really nice features around being able to leverage like snapshots of EBS volumes and some of that kind of stuff. So it's good to keep that in mind when we talk about this stuff. So let's visualize. What does a Fusion cluster actually look like? So this is a minimal HA config on AWS all in one region. You'll see we have 3 AZs and color-coded per Kubernetes resource. So yellows are Kubernetes services. Blue and green are deployments and stateful sets. And then the orange are containers per pod. So what we're looking at here, starting at the bottom, we've got our Zookeeper service and stateful set, which is striped across the 3 AZs. So this is a 3-node ensemble. And then kind of working our way back up, we have Solar, API. In this case, API will kick out the Spark driver. So we're not running Spark here, but API on a 15-minute frequency will fire up the Spark driver in that container and run your aggregations and Spark jobs. We have other topologies that include running Spark as its own set of services within your cluster. We also then have the connectors, service, Fusion UI, proxy, and web apps. On the far right there, you see a pink box. That is an ingress. So we also use an ingress for each of our Fusion clusters. So switching back to Helm quickly. When we talk about a Helm chart, again, it's a set of YAML templates. And so we actually organize a YAML per Kubernetes resource per Fusion service. So what that means is if you wanted to talk about an API and the fact, if we go back here, an API has a service. Where is API? This guy has a service, and then a deployment, and then the containers, and then might have things like pod disruption budgets or other Kubernetes resources. Each of those becomes its own YAML file. What we're looking at here is the API deployment YAML. So this is the configuration for what the Kubernetes deployment would look like for our API service. And this is an abbreviated version. Things to note here, we're just jumping into the section where we're defining what the containers are. You'll see this include here. This is, again, using a powerful templating language, this allows you to then include a template from somewhere else. This is including a sidecar logging container. So in our pod, we run 2 things, the API service itself and then a log shipper. So the next part is actually defining the Fusion container. And so we standardized on naming the container Fusion just so that it's easier to do kubectl commands. Once you have multi-container pods, you need to specify which pod you're interested in. And so it was just easier to standardize on calling stuff Fusion as opposed to API, UI, Spark Master, Spark Worker. It just simplified some of the CLI commands. So you can see we've parameterized our image, the image pull policy. We're defining ports, volume mounts, and envars. Another thing to take note of here is down here, we're passing in, the API needs to know where ZK is. This template, fusion.zoo.service name, what it will do is at chart install time, will resolve or evaluate that variable and automatically insert the appropriate pod name for ZK. And so that's some of the power and benefits of using Helm, is you can just connect these things and reference them as variables, which will get resolved at, again, Helm install or update time. So also the way this works is you can see, again, a bunch of variable declarations, YAML, where do the variables get defined? So a Helm chart is made up of templates and then a values.yaml. This is an example of the API section of the values.yaml. You can see we're specifying a few things. This one is pulled from a dev cluster, so our replica count in this case is 1 as opposed to 2, like we saw in the visualization earlier. We're defining the actual Kubernetes service here. We're saying, hey, use cluster IP, which is the default service type in Kubernetes. Cluster IP, for those guys that aren't familiar, means within the Kubernetes cluster, every service will know the IP of every other service, at least its internal address. Those IPs are not externally available, but if you go into a pod and list all of the envars possible, you'll see envars that represent every IP of every service running in your kube cluster. So this is one way that we got IPs to be, or DNS to work within for our Fusion clusters. Also defining resource limits and requests here. Some elevated numbers, again, because in this case, API will kick out a Spark driver, so we need to account for that kind of memory and resources being available in the container. JVM options, and then also of interest, we're setting the node selector here. A node selector allows you to select the type of node or instance, EC2 instance, if you're running on AWS, that you want this container to get, or this pod to get scheduled onto. So in this case, we're saying, hey, run one that has any value fusion for the label lucidworks.io/application. We also might have like one called Solar, if we wanted to run Solar that uses a different type of storage, say, than API, right? So you could actually, if you're running a heterogeneous mix of nodes in your cluster, you could target different ones for this pod to be scheduled onto. And then what does this look like actually in Kubernetes? So when you do a Helm install, it will return a name for the instance of the chart that it deploys. That name usually takes the adjective - animal form that is kind of familiar out there. So you get names like Happy Hippo or Hungry Tiger, or in this case, Ardent Manatee. And so I went and we just did a quick get pods here and grepped. It was just simple and easy, but just to show you guys, hey, this is running a fusion. This is what it would look like. So again, prefixed by the Helm chart name and then all the different services that are running. Another really interesting thing here, you can see that we are 0 for 1 and completed on the Fusion Web Apps post create support user. What this means is Helm allows you to also run Kubernetes jobs or any type of Kubernetes resource. And so that's a pretty powerful thing. And what we did here is after our Fusion cluster is ready and the right liveness and readiness probes and health checks are successful, we then go ahead and create a read-only support user for this cluster by a RESTful API command. So we just define that in like a small busybox container and tell it to go run this against the Fusion cluster. So you can use those types of tools. And you also see the 2 out of 2 for each of these, and that's because there is 2 containers per pod. There's the actual service plus the log shipper. So that's why you're seeing 2 there. And then, of course, same thing for get ingress. This is the actual ingress that was created. This was out of our dev cluster, so don't try to hit that URL. You need VPN access to get there. But I'm going to turn it over to Joe now.
Thank you, Alan. Mm-hmm. So I want to talk a little bit about the state of kind of Fusion scaling in general across all of our various services. So the 2 that are kind of easy, we have Zookeeper and the log shipper. They're both static, right? So like, hey, we run a 3-node ensemble Zookeeper. Given that we don't share Zookeeper across a bunch of different clusters, each cluster gets its own Zookeeper. 3 nodes is totally adequate for any needs a single Solar cluster will have, right? Since they're not shared, it's totally fine. And obviously the log shipper is really more of a sidecar, right? So it'll run alongside every single node that it needs to collect logs from, but it doesn't really have any kind of scaling needs. A lot of our services are horizontally scalable. So API, proxy, and UI, right? They're all stateless, right? They take in commands and they issue out commands out to other resources. So it's totally fine. They can just scale up and down as appropriate inside a Zookeeper. The Connectors Classic stores all of its state inside of Solar, right? So all the visited entities it needs to store is stored inside a Solar collection. So it can also scale up and down because it also doesn't take any internal state. It has state, but all that state is stored inside of Solar. It makes use of our backend storage to achieve that. The web apps also really doesn't have a lot of state. It's just serving up HTML files. They'll get changed and uploaded as appropriate. Today, they do require a sticky load balancer because of the way they handle session, but we're planning in Fusion 4.3 to fix that issue. But if you go deploy it today, they'll need a sticky load balancer in front of them. And then obviously Spark Worker and our SQL, they scale horizontally if you're not running a job. If you are running a job, that's not the way Spark scales, so don't try to do that. But like, hey, if you realize, hey, I'm about to need to go run a big workload, you can spin those guys up, do a bunch of work, spin them back down. They scale up and down as appropriate, but not in the middle of a job. That's not the way any of this works. So the 2 that today are hard to scale is obviously Solar, right? So it's a database, right? It contains a bunch of state, and each node contains very probably different state than every other node, right? Because it contains different shards from different collections, and knowing what goes where is very, very difficult. And like when you think about, hey, what is my activity to add a new node? Well, I add a new node, and then I need to figure out what shards from what collections need to go on this new node. And hey, do I need to, hey, I'll have to go look at the state of all the other nodes in the cluster, and I have to go determine which those nodes are hot. And hey, do I have enough? Maybe I actually need more shards, right? Because I need more query capacity, and so I need to go increase the replica count so I have more shards. It's a very complicated process. And today, we don't have any of this automated, right, inside of Kubernetes, so it's very, very difficult. And scaling down is even harder than scaling up, right? Scaling up is at least we'll add nodes and then we'll figure it out. Scaling down is well, now I need to shrink nodes and maybe merge cores, and that stuff gets really, really complicated extremely quickly. Solar Autoscale has a pattern that we want to make use of that we think will solve some or all of these problems when combined with operators, which I'll talk about in a minute. But that's an upcoming thing. That's not a right now thing, sadly. And then our connectors classic, it stores all of the visited entities locally, right? So if you go crawl a web page or you go read rows out of a database, it has to mark, hey, I've seen this row or I've seen this entity. And so, if it loses its backend data store, it can either be very painful or not painful depending on how large your corpus is, right? If your corpus is a couple thousand documents on a web page, maybe recrawling them isn't that bad. If your corpus is 1 billion documents and recrawling them is really expensive, that can get really painful. And Connectors Classic, it stores all the data locally. So if you have multiple data sources, you could assign those data sources to separate Connectors Classic nodes. But that's actually a manual process, that assigning, so it's actually kind of painful. So obviously, scaling that is very painful, which is why we created the Connectors SDK, which we're slowly moving all of our crawlers and all of our related document collecting activity to, because it's intentionally designed for scale, and the Connectors Classic really just isn't. So let's talk a little bit about things we're planning on doing, both internally and exposing to a lot of you in the future. So, we have a lot of lofty goals for Fusion. I think that would not surprise anyone. But I think one of the things I'm the most excited about, because I'm like a lot of you, for Lucidworks, I run Fusion for them, right? So I'm very concerned with how easy it is to work from a DevOps standpoint. And I think it's fair to say that our DevOps story is evolving, and we have a long way to go. And I tell them that constantly. And so there's a lot of goals to both enable me and to enable all of you to be able to do operations easily. We want to enable everyone to do operations easily inside of Fusion on any cloud platform that you might want to run us on, right? And we have lots of use cases to run on various cloud platforms internally as well, right? So let's talk about some concrete things that we're looking at doing that will hopefully make my life and some of your lives easier. So we're getting ready to release an official Fusion Docker image. It will release alongside every Fusion release. The first one will be alongside 4.1.1. It's stored in Docker Hub, and after the 4.1 release, you'll be able to do a Docker run, map the UI port, which is that port right there, Lucidworks Fusion, and then you'll have a full Fusion node running locally on Docker. It'll run all the services. It'll be ready to go. And the next step, obviously, from there is a compose, which will be reference architecture for kind of running each service kind of in an isolated fashion, right? So hey, I just want to run a node that has API on it. Cool. Here's a Docker compose that explains to you how we would do that, and you can turn around and apply that to your Mesosphere, your Rancher, your Helm, whatever deployment mechanism you want to use. Since we use Helm internally, we're also going to release a Fusion Helm chart that will kind of be a fully featured reference architecture. We'll support a variety of topologies via parameterization, and we'll also support a variety of locations, right, like environments via parameterization, right? So if you want to run this in EKS or GKE or AKS or OpenShift or wherever you want to run it, right, we want to support you running it there, and we want to support us running it there, right? That's our goal. Also, let's talk about Kubernetes operators. Who here is familiar with what an operator is? One person, cool. So for those of you who listened to AB's talk a minute ago, operators follow a very similar interaction, like feedback loop cycle of they observe the universe, take an observation of the universe, act on that data, analyze what just happened based on the actions, and then take another observation of the data, and then act again, right? So it's like a constant feedback loop as we add in more data. And so some of the powerful things about operators, right, is they are like an automated SRE specifically for the thing that you care about, right? They have baked in operational knowledge. They have a nice level of lifecycle management, very similar to Helm, where you install, delete, update kind of at the full cluster level. And they allow you to do metrics-based decisions. So one of the things we're going to be working on and open sourcing once we're ready to go is a Solar operator, right? So it'll be purpose-built for Solar. It'll be making use of the Solar auto-scaling framework to help make appropriate decisions, right? So as I was just talking about, right, Solar does a lot of these internal measurements already because of the auto-scaling framework. And so we're going to take advantage of those decisions to bake this knowledge into a Kubernetes operator, right? So it'll be able to shard split up, add more servers, scale down servers, rebalance shards, do all that kind of fun stuff, right? And really what we're chasing here is the thing that was talked about at last Revolution is what it was called last time, which was like the ideal cluster state, right? You want to make sure you don't run out of disk. You want to make sure you have your queries are at a certain speed. You want to make sure all your system performance is appropriate level. You want to make sure that you're stable and performant, right? So that's what the goal of this operator is going to be. Making use of all the metrics that are collected by Kubernetes and all the metrics that are collected by Solar today about its state. And also we'll perform backups because that is a very important activity that is also very complicated. On top of the Solar operator, leveraging the Solar operator, we're also going to build a Fusion operator. And the Fusion operator will make use of all the fact that a lot of our services horizontally scale to very easily spin up or spin down as appropriate for those various services. Right, we'll make use of we'll leverage the Solar operator to make use of it. We'll have some kind of answer for how we manage the connectors classic as well, because it's also one of the painful points of our environment. And so those are all things that we're starting to talk about internally. And once we have them, we'll be sharing with all of you. I also want to talk about some recent and upcoming features in Fusion that are less Kubernetes focused and more kind of DevOps-y focused in general, just so everyone's aware of them. So we have log shipping, which is Alan was talking about before, where we want a log shipping container alongside every Fusion node. It's actually using Fusion to do the log shipping. Fusion uses Logstash internally. If you just spin up a Fusion cluster, right, you'll actually be collecting logs and shipping them to a local collection inside of your Fusion cluster. But you can very easily configure it by just changing what ZK it needs to talk to and what the collection name it needs to go to talk to a remote node. It's very straightforward. This is in the Fusion.properties. It's very easy to configure. And then you can turn around and start collecting logs from a variety of different clusters inside of Fusion. Inside of our analytics view, you can take a look at all the logs that we've collected. Right, you can see, hey, all the services that are running, log levels, all that kind of stuff. You can click on all these and get filters on them. This is based on Banana, which is a product that we have apparently. We're also in 4.2. We're also going to start metric shipping. We're going to use the same collection mechanism as our log shipping. We're going to, again, store metrics locally. They can be shipped to a remote cluster. You can do the same kind of analytics, right? Because Solar is a complicated search engine, right? If you want to then write queries against Solar to determine what's the state of the metrics, it'll be very straightforward, assuming you know Solar. And it'll also allow us, on a thing I'll just talk about in just a second, to start collecting data and start displaying internal information about the cluster, right? So like we'll be able to say, hey, this is your disk level and your CPU level for this specific node over the last unit of time, right? That's some of the kind of data that we'll be collecting. And so we also are coming out in 4.2 with the DevOps Center, right? So this will collect and visualize a set of key metrics that are very important to the Fusion cluster as a whole. Kind of a central place to determine the state of the cluster. It has a couple nice views of kind of like the cluster's own status. Some of the metrics today are synthesized, right? They're not actually directly available from some internal state. We're working on making them not be synthesized, so you could theoretically just pull all of these if instead you want to pull this data into Prometheus instead of running this thing locally, but that's a direction that we're moving. And so the kind of thing you'll be able to see inside of Fusion is like, oh, hey, I see a query rate jump up because of a user jump, and hey, I see a equal amount of signal volume jump up. So you can kind of see, oh, hey, over the last unit of time, I noticed something interesting happened. Let me go investigate what occurred and see if there's any kind of problems. We'll also be able to track the state of all the instances that we have, and you'll be able to kind of tell like, oh, okay, hey, I have a couple solars that are good. I have one solar that's kind of low on disk. Maybe I need to go investigate him. This will be useful for kind of comparing, hey, I think my state of the cluster looks like this. Hey, Amazon thinks my cluster state looks like this. Let me go compare them, right? Because like the comparison point is where it's really interesting, right? Like, hey, Fusion thinks this thing, Amazon thinks this thing. Okay, cool, let me go figure that out. We'll also add a new view into the logs so it doesn't look quite as dated. So that's all that I got. Questions?
You talked about the solar and Zookeeper stack. Do you run a Sunday solar and Zookeeper cluster per availability zone, or is it split? Is it shared across?
It's shared across all 3 availability zones.
So per region, you have one solar cluster.
Well, so we deploy. Well, it's like on my team, right? I manage Fusion deployments for multiple customers, right? So like an individual cluster will be split across 3 availability zones, right? For uptime reasons mostly, right? And so the Zookeeper will be striped across all 3.
So you just do indexing to one region, so you don't have to.
Yes, we do not do multi-region. Yes.
Kube clusters across regions today is hard.
Yeah.
So that's more of a Kubernetes question, what you can do with your infrastructure there as opposed to what we can do with Fusion. First, Kube has to have, like, at that point you're into, what's the word?
It doesn't work.
Yeah, it doesn't work.
It just doesn't work,
yeah. Federated. At that point, you're
Yes.
in federated Kubernetes land, and the federated stuff they've abandoned
Yeah.
at this point. And so, we're all waiting on that answer too.
Yeah, I mean, like if we were going to take that approach today, right, we'd do some kind of like CDCR between both, right, is the honest approach that we would take. If we're like, hey, we need to have 2 masters in 2 different regions, that's the approach we would take.
If you want to add new pipeline on the Fusion that call outside services,
Mhm.
how would you architect this with your infrastructure in Kubernetes? So do you have other services as a part of your Docker or?
So if we wanted to call a shared like NLP service, absolutely you can do that. I mean, there's no reason you couldn't have your config your Fusion to point to some URL. There's interesting ways you can do that within Kubernetes, where you can actually set up Kubernetes kind of alias resources that if that thing is also running in your kube cluster, it can talk to it directly without having to like leave. It can stay within the kube network is the simplified answer. So yeah, that's not a problem.
Could you elaborate on how you persist the data? So in an instance where a node goes down or a pod goes down, how do you recover the data?
Sure. So one second, spilling up my brain. Excuse me. So all of our nodes are backed by EBS, and so the way stateful sets work, right, is the stateful set manages an EBS volume for each node, and so when the Kubernetes node goes away and gets spun back up, Kubernetes says, cool, this is a replacement for this specific stateful set node. Let me reattach the EBS volume, right? So we depend on functionally Amazon's infrastructure to keep our disks around when the node goes away.
Right. So specifically, the way stateful sets work is you have a pod, and they have an identity. So this is how, when they were called pet sets before, I don't know if you guys have heard this story before, but they were called pet sets because generally Google thought of containers as cattle, and if a cow dies, or it's ready to die, you just shoot it in the head and replace it with another one. And a pet was something that you valued and you cared for and you fed it, and so it had an identity that you were very, again, cared about. So a stateful set also maintains that identity, right? And so if you run a stateful set with 5 replicas, each of those replicas has an identity. So it would be like solar-0, solar-1, and on and on and on. Each of those is backed by its own EBS volume. And then, so if your solar-0 container actually, or pod goes away, it will get replaced by another Solar-0 that connects right back to that same EBS volume.
And that has the same node name and
Yeah.
DNS.
Yeah.
Exactly.
Yes.
Yep.
Guaranteed.
Yep.
So that answers my first part of the question. What happens when the pod goes down? Essentially, the whole farm is gone.
When all of Kubernetes is gone,
No, the pod.
uh,
Because the stateful set will cover what's inside the pod, and once that pod's life is gone, how do you recover the data?
you can set there are flags you can set around what to do with the volumes based on the life cycle of the stateful set. So if you say keep this volume around for audit purposes or whatnot, you can do that. Does that answer your question? Yep.
Have you done any benchmarking when you say the solar cluster is split across multiple availability zones, when there is a recovery of data, say terabytes of data, it spawns across multiple zones? Did you see any performance degradation?
So we have seen performance degradation when the cluster decides it wants to copy a massive amount of data across the availability zones. And a lot of that is related to the way like Solar and Lucene view disk. They kind of view it as an infinitely large stream that they can just pull as much from as they want. And so obviously we ran into some interesting issues related to like EBS like rate limiting us because we're hitting the EBS service too high because we're having data copying across availability zones, or really just data copying across nodes in general. Like in a lot of ways, like the availability zones, you kind of don't notice, right? They're kind of they're fibered together, right? So you don't really notice a difference between availability zones. In all honesty, none of our tests have ever shown us being able to detect any kind of variance between availability zones. But what we do notice, hey, we got throttled by EBS, and they're like, hey, you can't have any more EBS until you stop. That's mostly what we saw. We didn't actually see availability zone differences.
Can you talk a little bit about health checks and what the future of health checks are for Fusion today? At the service level, they're done through the agent. There's something that's going away.
So no, it's a good question. So are you guys familiar with in Kubernetes, there's the liveness and readiness checks? So we are using something internally right now that we refer to as agent-based health checks. As we go forward with our more public offerings around Docker Compose and Helm charts and all that stuff, we'll have references for all of you guys to hit the appropriate health check endpoints. I'm not going to go any deeper than that right now, but it's coming. So we'll have.
Differentiate between live and ready.
Yes, absolutely.
Yep.
Yep.
Does ready include warm up? Like in traditional, we have like ring up and warm up.
We are talking about showing more granular statuses of where the Fusion service is, rather than just I am ready. So liveness, if you're not familiar, liveness is this container there? And then readiness is your app actually ready to serve traffic or serve requests? And he's asking, is there a more granular way of knowing? Is it ready? So the answer is yes, that's coming.
Yeah, like hey, are all the blocks in RAM yet? Yeah,
Like-
exactly.
Yep.
How much of work you are done in GCP, or this is all done in AWS so far?
We are in AWS running in production, again, on a COPS-based cluster. I would urge you guys not to roll your own, and just so you also, that's not just me saying that. I've been at DockerCon, Container World, Jenkins World. I'm hearing all the same messages. So, yeah. So we are in GK as well, and we're going to be, again, more public stuff coming soon. So Joe mentioned it. My team is also, in addition to having Helm charts and stuff, we're going to be also having reference materials for if you want to run on VMs in GCE or just in EC2, and you want to spin up a demo or production quality Fusion cluster. That stuff's coming. So our
That's traditional, right?
yeah, that's VM based. So, but yes, GK, you should install Helm to play our Helm chart. Yep. We're in AWS, GKE. We have OpenShift as well, also.
So if I need to do it now, if GCE is where I'm going right
Yes.
now, and
Yep.
then eventually GKE.
Yep. It's not far off.
So if I need to horizontally scale just solar modules real time, so how would I do this in Kubernetes?
Well, that
Not even automatically, but even manually. I want to
So if you just want to add nodes, you just run
I
a,
want to add just solar node itself.
that's a simple kubectl command. Or it's actually a Helm command. It's a Helm update, and you tell it, you just give it more replicas.
Right.
Tell it to your solar stateful set, more replicas.
So and it will create more pods and it's connect them.
It's the same pod. We'll add more containers or replicas.
Yeah, more,
Yep.
yeah.
Yeah, then you also have to go do all the manual work of like rebalancing, right? Because obviously you just added more resource, right? Unless you're going to automatically create new shards and collections that we put on there, you'll have to rebalance in some way.
It's not like stateless type auto scale, right? It's
Yeah.
Yes.
to
No, no,
write
it-
data.
This
and
is, yeah.
solar will never be
It's like
stateless.
Yeah.
Solar, yeah.
Yeah,
Yeah.
solar will never be stateless auto scale. It'll always
Yeah,
be
yeah.
complicated.
And that's where the value of like producing an operator really is going to allow you to say, hey, add one of these guys, and it will just do the right thing. So
What is the time frame on the operators?
operators 2019 at some point. The other things we're talking about are probably Q1-ish. Like, so those are those are going to be sooner. But the operators we're going to start development soon.
Do you do any sort of replica placement logic for solar?
We're going to have to. We're going to have to as part of the operator.
And you, because I'm guessing Kubernetes is putting environment variables of where an instance is running or something like that, and you use that.
Yeah, you'll be able to find out from the Kubernetes itself, like, hey, what AZ is this running in, so you can make sure that like your shards are in the right split and all that kind of stuff. Yeah.